classical mechanics problems. And as you know, it's also a competition. You can take part in the competition by filling the Google form, okay, which will be given in a small window of 5 minutes in between the lecture. Right? We'll have a 5 minutes break in between. You will get this link. Those of you who fill the form will get a problem through email. You can just solve it and send it back and win attractive prizes. Okay. All right. So with that, let me start with our next problem. Okay. So here is the problem. The Hamiltonian of a relativistic particle. Okay, so we are talking about a relativistic particle of mass m and momentum p is given by, this is the Hamiltonian. All right. The Hamiltonian is given in units in which the speed of light is 1. So we have taken the unit where speed of light is 1. The corresponding Lagrangian is, okay. So the quick answer, the quick way to do this is to know the relativistic Lagrangian. All right. We should know that the relativistic Lagrangian is given by minus m square root of 1 minus v square by c square minus v of x. Okay. This is the relativistic Lagrangian. Right. Now this is the quickest way to do this, but you may not always remember you may not always remember the exact form of the relativistic Lagrangian. And if not, you can easily solve this. All right. You can easily solve this. All right. So the answer is indeed option B, right, where c is equal to 1. Now how do we solve this quickly? Okay. So we know that the Legendre transformation connecting the Hamiltonian and the Lagrangian can be written as x dot p minus L. Right. In other words, this is just one dimension, so we don't have a summation. We have just one variable x and corresponding conjugate momentum p. Okay. So correspondingly, we know that L is equal to x dot p minus h. So that's how we plan to solve this problem. Now, how do we get this x dot? Right. We use the Hamilton's equations. We see that x dot is equal to dou h by dou p. These are Hamilton's equations of motion. All right. So the time derivative of x is given by the derivative of the Hamiltonian with respect to the momentum. Okay. So x dot equal to dou h by dou p, and we just take a derivative of this with respect to p. Right. And what would that be? That's 1 by 2 square root of p square plus m square multiplied by 2p. Okay. You first take this derivative and then you have got this. So this is equal to p divided by square root of p square plus m square. Okay. That's x dot. But we shouldn't have any momentum in our final expression. Lagrangian is a function of x dot and t generally, not a function of p. So you will have to, wherever p appears, all right, you will have to write it in terms of x dot. So for that, we just invert this equation to obtain p, all right, in terms of x dot. That's what we do next. So we square on both sides. We see that you just square this on both sides, all right. We have got x dot here. You just square this on both sides. So x dot square is equal to p square divided by p square plus m square. Okay. And you can easily, so I think I will use a fresh page here. So we have got, this is where we stopped. We have got x dot square is equal to p square divided by p square plus m square. Okay. We just take it from here. Okay. X dot square is equal to p square divided by p square divided by p square plus m square. All right. Now we just solve this. Okay. X dot square is equal to p square. Okay. Now you just solve for p. All right, and you just rearrange this and you get p square as m square x dot square divided by 1 minus x dot square. All right. So that's the momentum for you. Okay. Now this is the square of the momentum. The momentum would be m x dot divided by square root of 1 minus x dot. All right. Now you might immediately recognize this as the usual relativistic momentum. All right. P is equal to gamma mv. Okay. P is equal to gamma mv. All right. Where gamma is equal to 1 by square root of 1 minus x dot square by c square. We have taken c equal to 1. Okay. So this is the relativistic momentum, and so this is why we use that particular expression as the relativistic Hamiltonian. Okay. So we have got the relativistic momentum. So in order to make it convenient, we will also find p square plus m square. All right. P square plus m square is equal to, just square this and add, and you will get this as m square divided by 1 minus x dot square. All right. Just add m square here. Alright, you just add m square here and you'll get p square plus m square. Okay. Alright, now we write expression for the Lagrangian, that's x dot p minus h. Alright, and that's equal to, we just make this, we have got p here, alright, so x dot p would be simply m x dot square divided by square root of 1 minus x dot square minus the h given h is m divided by square root of so we have got p square, we have already found out our p square plus m square, alright. We have already found out our p square by p square plus m square. Here we just substitute that, alright, the square root of that. So it's m divided by square root of 1 minus x dot square minus v of x. Alright, if you don't remember, the Hamiltonian is given like this, h is equal to square root of p square plus m square minus v of x. Okay, so we just substitute it here, right. So instead of square root of p square by m square, we have got this m square divided by 1 minus x dot square. Now it's done, alright. You just simplify this and you'll get the Lagrangian as minus mc square square root of 1 minus x dot square by c square minus v of x, alright. And usually as part of our course, when we do the relativistic mechanics, we'll study this expression, we'll obtain this expression, alright. At least we'll motivate this expression as the correct relativistic Lagrangian. You see that it does not have the form t plus v, alright. You notice that it does not have the form t plus v. Okay. So the Lagrangian, this is the relativistic Lagrangian, and this has, why do we choose this as the relativistic Lagrangian? There are different reasons, alright. One nice motivation is that if you take dou L by dou x dot, you will get gamma mx dot, the usual relativistic momentum. Okay. So that's one reason to do that. There are other ways to motivate this, but at the moment this is the answer to our question. Okay. Alright, let's go to the second problem. Again, it's a problem from relativity. There are so many problems being asked from relativity, alright, and the problems are quite simple if you notice, alright. See, this problem, it's quite simple. It's just the one way to do is that you remember the Lagrangian, relativistic Lagrangian. Another way to do is that you solve it on the spot, right. Any which way, it's quite easy. So if you have a good understanding of special theory of relativity, there are a few problems that you can always solve, at least a couple of problems, alright. Okay. So this is alright. So this is for the next exam, the net exam. This was given, right? And at that time, right, many people could not answer this question, right? Even in some of the online notes which appeared, this problem was said to be unsolvable. That's because people did not really study this part of special theory of relativity. Okay, so this is a new. This was kind of a new kind of a question from special theory of relativity, different from the usual pattern. Well, let's look at it. It's quite a simple problem. What's the proper time interval between the occurrence of two events if in one inertial frame events are separated by 7.5 into 10 raised to 8 meter and occur 6.5 seconds apart, right? And they have asked the proper time interval. Now, the usual expression that comes to our mind when we talk about proper time is this. We said that delta t is equal to delta t0 divided by square root of 1 minus v square by c square. But we need a velocity to solve this problem, right? So it seems that you don't have enough information to solve this, but there is information hidden in here, all right? I'll tell you how. That's one way to do it, or you could directly think about there's this quantity, one of the most important quantities in special theory of relativity, ds square. Okay, it's known as the invariant interval. It's given as c square dt square minus, I'll write it in terms of delta. Okay, we can write as delta s square is equal to c square dt square minus delta x vector square. Right, by delta x vector square I means delta x dot delta x. Okay. Now, this is the geometry of space-time according to special theory of relativity. This equation gives you the geometry of space-time according to special theory of relativity. You can immediately compare it. This is because we are talking about a four-dimensional space-time. You can immediately compare it with the usual Pythagoras theorem. We will have ds square is equal to dx square plus dy square, right? If you have a plane like that and distance between 2 points, in order to find that, you just need to get this dx and dy, right? And then you can use the Pythagoras theorem. That's known as Euclidean geometry, but space-time does not have Euclidean geometry. It has a Minkowski geometry. Okay, so this is the geometry of space-time. Now, what's importance of this expression? Let's just rearrange it a little bit. All right, we see that delta S square by C square is equal to, we'll pull this dt square outside. Okay, 1 minus, sorry, I should write a delta here. So, okay, so that would be, you pull this delta t square outside. Okay, I am dividing it throughout by c square also. Right? So, this delta t square 1 minus delta x by delta t square. Okay, and there is 1 by c square here because we pulled out the c square also. Right, or we can maybe write one more step. I will pull the c square delta t square outside. So, there is a 1 by c square there also. Okay. Now, what is this? You see that delta s square by c square is equal to delta t square multiplied by 1 minus, what's this delta x by delta t? That's a velocity. Alright, so it is v square by c square. Okay. Now, you see that we get back the expression for proper time, because if you take square root on both sides, you see that delta s by c is equal to delta t square root of 1 minus v square by c square. Right. So, we can use this formula now. Okay. So, if you find the invariant interval, by dividing it by c square and taking square root, you can find the proper time. We know that this is the proper time, because as we said already, we know delta t is equal to delta t0 divided by square root of 1 minus v square by c square. That's usual time dilation formula. So, this part is called as the proper time. So, you see that delta t0 is equal to delta t square root of 1 minus v square by c square. Okay. So, what I have shown here is that you can find the proper time from the invariant interval. Right. So, this is the expression that we start with, and there are many problems that we can solve quite easily using this formula. Right. So, that's the formula that we need to work with. Okay. Given that formula, let us see how to solve this problem. Okay. So, first we calculate this quantity from the given information. All right. So, let us see, you see that, let us calculate delta s square by c square is equal to delta t square minus delta x square by c square. Right? We divide throughout by c square. Now, we just substitute the quantities given. All right? Delta t is given to be 6.5 seconds. All right? The time separation between the two events is 6.5 seconds. All right? So, that is in SI units, do not worry. So, that is 6.5 square means delta x square by c square. So, that would be 7.5 into 10 raised to 8 square, because that is delta x square divided by c square. So, I will write it as 3 into 10 raised to 8 square. This 10 raised to 8 gets immediately cancelled. Okay. So, this is basically 6.5 square minus 7.5 divided by 3 is 2.5 square. Okay. Now, this is just a numerical calculation. You do this with the numerical calculator. You can do it in different ways. Right. You do not have to square and add. You can just add these things different. So, this is, you know, this is of the form a square minus b square. Right. You can just find 6.5 plus 2.5 multiplied by 6.5 minus 2.5, right, and that would be 6.5 plus 2.5 is what is it? It's 9, yes, okay, and 6.5 minus 2.5 is 4. So, that is equal to 36. What is 36? This is delta s square by c square is 36. We know that the square root of this is the proper time. That is what I just showed, right. So, the square root of this is equal to, so you see that delta tau is equal to delta s by c, that is equal to 6 seconds. That is the correct answer. So, we have got that answer here. It is option B. Okay. Quite a simple problem if you know that, if you know this expression, all right, this expression and its relation to proper time. All right. So, here is yet another problem from special theory of relativity. The muon has mass 1.5 MeV per c square. Right? So, the mass is given in terms of energy E by c square. Okay? The units work out, and the mean lifetime 2.2 microsecond in its rest frame. Right? 2.2 microseconds in its rest frame. The mean distance traversed by a muon of energy 315 MeV. Okay? Before decay is approximately. What is the mean distance travelled by a muon of energy 315 MeV? All right. So, it's given, the mass is given, all right, the mass is given us. So let me just write mass. We have just one particle. I'll write the mass of the muon as 105. So I'll write it as, or we can write it as, okay, the rest energy mc square is equal to 105 MeV, right? The rest energy mc square is equal to 1.5 MeV. Oh, sorry, 105 MeV, right? I've just taken this C here, so this is mc square. Okay. Now this is the rest energy of the muon. This is known as the rest energy. E is equal to mc square is the rest energy of a particle, right? And now we are said that there is a muon of energy 315 MeV. 315 MeV. So we have got a muon of energy 315 MeV. Okay. But we know also that the relativistic energy is equal to gamma mc square. Relativistic energy is gamma mc square. This is all we need actually. The relativistic energy is gamma mc square. We already know mc square, that's equal to 105. Okay. So you see that 315 is equal to gamma multiplied by 105, or gamma is equal to, you just solve this and you get gamma is equal to 3. Okay. 315 divided by 105 is just 3. Okay. You get gamma, that's not enough, but we can do part of the problem from here. Okay. So it's given that delta T0, the proper what do you say, the proper lifetime in the rest frame of the muon, we know that delta T0 is equal to 2.2 into 10 raised to minus 6 seconds. Okay. So the corresponding frame, the corresponding time, the lifetime as observed from a frame corresponding to gamma equal to 3 would be gamma delta T0. So it will be simply 6 because we already found gamma, that's 6.6 into 10 raised to minus 6 seconds, right? But that's not all we need. We got the time, we got the lifetime of the average lifetime of the muon as observed from this frame, okay, the frame in which this muon has energy 315 MeV. All right, we did this. Okay. Now we also need the velocity. So in order to find the velocity, again you can solve this. We have got gamma is equal to 3. So 1 by what's gamma? We just square on both sides. Also from here we need to find this. Okay. So gamma square is equal to 9, which means that 1 by 1 minus u square by c square is equal to 9. Okay. Now we can solve for u square. Okay. Or you can solve for u. You just invert this and solve for u, and you get u as, okay, you just do this, it's easy. You get 2 root 2 divided by 3c. Okay. This is the speed of the muon. Right. Now you are looking at a muon which is traveling at this speed. Okay. And we know that in this frame, this particle, from our frame, this particle has a lifetime delta t is equal to 6.6 into 10 raised to minus 6 seconds. Okay. Now the question is, what's the distance traveled? Right. The mean distance traveled. What's the mean distance traveled? So we have got the velocity here, we have got the lifetime of the muon. Okay. So we have got velocity and we have got lifetime. Now we just find, because we know that, okay, because we know that I'll write here, v is equal to distance by time. So distance is equal to velocity multiplied by the time interval. Okay, we have got the velocity, we have got the time interval, you just multiply them. Okay, so the mean distance traveled would be u multiplied by delta t. We have got both of them, you just multiply it to get, it appears the final answer would be, okay, you will see that it's equal to 1.86 kilometer. Okay, it's 1.86 kilometer. The final answer is 1.86 kilometer. Okay, for some reason this option is not, this answer is not one of the options, but the nearest one is 1.98 kilometer. Or the nearest answer to what we obtained is 1.98 kilometer. Okay, so that's the option that you have to choose in such cases. Okay, I hope it's clear. It's quite easy. I'll just explain what we did. Okay, the rest mass is given. The rest mass is given, or the rest energy is given. Right, and and then we are talking about a muon which has energy 315 MeV. So we know that it's moving. So we see that E is equal to gamma mc square. From that we found gamma, and from gamma we found the velocity. Alright. Now using gamma we also found the lifetime as observed from this particular frame. That would be the proper lifetime multiplied by gamma, and we got the lifetime also. So we got the lifetime, we got the speed at which it's moving. Now you just have to calculate, okay, how much distance this will travel. So you just multiply the velocity by the lifetime of the muon, and that you get the average distance the muon will traverse. Okay, and it's said approximately. Alright, so approximately, this is the catchword here. So we got 1.86 kilometer and we have got 1.98 kilometer in the options. So that's the correct option. Okay, sometimes you may not have the exact answer in your options. Okay, and yet another problem for relativity: the area of a disk in its rest frame. The area of a disk in its rest frame S is equal to 1 in some units. So it is 1. Okay, the disk will appear distorted to an observer or moving with the speed u with respect to S along the plane of the disk. Okay, why? Because of length contraction. Okay. So if you are looking at a perfectly circular disk, okay, which is at rest, it's perfectly circular, fine. But if it is moving, right, suppose if it's moving in this direction, then this length get contracted, right? If you are looking at a moving disk which is moving like this, then instead of a circle you have an ellipse. Okay, now instead of the area of the circle is given by 1, okay, in this reference one it's given equal to 1 in some units. All right, so the area of disk measured by the observer, or what's the area, what's the new area. All right, this area is 1, what is this area? That's the question. Okay, the simple answer to that, the area can be written as you know the length contraction formula, right? You know the length contraction formula. Okay, L equal to L0 multiplied by square root of 1 minus v square by c square. Here it's u square. Okay, and this length contraction happens only in the direction of motion. So there is only length contraction in this particular direction. There is no length contraction in the perpendicular direction. All right, so this length alone changes, and correspondingly you can easily show that the areas always change in this form. A is equal to A0 square root of 1 minus u square by c square, because this is a constant. This one square root of 1 minus u square by c square is a constant. This is the result you will get. Okay, so you can from here you see that the answer is option A. All right, now if you are not convinced by this, you can just do this. All right, because let's say that this disk has radius A. So the area of it is pi AA in the frame in which the disk is at rest. Okay, this is pi A square, usual area of the triangle. Right? Now what happens when it is moving? It becomes an ellipse. This distance does not change, it's still A. All right, because this the distance perpendicular to the direction of motion does not change, it is still A, but this distance changes, it's equal to B, it has reduced. All right, so this becomes pi AA is given, right, this is the area of the circle. What's the area of the ellipse? Area of the ellipse is pi AB, and what is B? It is the shortened length, so that's equal to pi A square root of 1 minus u square by c square. All right, and we already know this is pi A square, the area of the circle, which is given to be 1 in some units. It's given as 1. So the answer is 1 multiplied by 1 minus u square by c square. So this is the correct answer. Okay. All right, I hope that's clear. And you can directly use this formula, or you can use the length contraction formula. You are not convinced by it. You will also see that volumes also change like this. All right. Volumes also will change like this, because there is only length contraction in the direction of motion. All right. Now I hope that's clear. We have come to our fifth problem. A system is governed by the Hamiltonian. The Hamiltonian is given. All right. Px minus ay square and py minus bx square, where a and b are constants and px, py are momenta conjugate to x and y respectively. For what values of a and b, okay, will the quantities px minus 3y and py plus 2x be conserved? That's the question. Okay, so this is, so you need to find the value of a and b. Okay, in such a way that, sorry, this is not px minus 3y, it's px minus ay, right? I think I already wrote the answer. So px minus ay and py minus bx, right? I apologize for the mistake, right? So we need to find a and b such that these combinations are conserved quantities. Okay, the Hamiltonian is given. We notice that the Hamiltonian has no explicit time dependence. That makes it easier for us. Now, how do we solve this? How do we solve this? So if the Hamiltonian has no explicit time dependence, etc., or the observable, the quantity that you are talking about has no explicit time dependence, then you should know this particular result. You can use Poisson brackets. Okay, Poisson bracket. Okay, so if this A has no any specific time, explicit time dependence, then A is conserved. A is a conserved quantity if the Poisson bracket of this quantity with h is equal to 0. This is what you need to do. This is what you need to know. Okay. So the question is, for what value of A and B are these conserved? So we check, we see, we have got okay, I'm sorry, I think I made a mistake again. The question was correct, alright, the question was correct. I'm sorry. Okay, A and B are inside the Hamiltonian. I'm sorry again. So this is the correct question, alright. So we have got the Hamiltonian. A and B are inside the Hamiltonian, alright. Now the only information given to us is that this quantity and this quantity are conserved, alright. Then what's the value of A and B? That's the question. Okay, so immediately we know that if, for example, px minus 3y is conserved, the Poisson bracket with the Hamiltonian has to be equal to 0. Okay, now you just substitute the Hamiltonian here. Px minus, these are Poisson brackets, all right. It looks like the commutator, but since we are dealing with classical mechanics, we'll just use the square bracket. Okay, px minus 3y, and you just write h here. Okay, h is half px minus ay square plus half py minus bx square. Okay, just so that we don't confuse it, I'll put a curly bracket here. All right. Now we demand that this is equal to 0, and that equation will give you the value of a or b. All right. In order to determine both, we need two equations. This will help us determine at least one. Right, or at least we will get two equations by demanding that both these quantities are conserved. Now let's check. All right, now let's check. Now the thing that you need to remember is the fundamental Poisson brackets relations. All right, xi with pj is equal to delta ij, which means that x with px is 1, x with py is 0. Okay, that's delta ij. If I equal to j, it's equal to 1. So if pj with xi, you will get a minus sign. Okay. Similarly, if it is xi with xi or xj, it's always 0, and pi with pj is also 0. This is the result we will keep in mind. Okay. Now, when we start doing these kinds of problems, it's always convenient to just write down only the non-zero Poisson brackets, only the non-zero Poisson brackets. So let's just check. We have got px minus 3y here, okay, and here we got px minus ay. Right. So we just check the Poisson brackets. Px with px is 0. Okay. Px with ay is 0. Px with x is non-zero, but px with ay is 0. And you see that y with px is 0. Y with y is also 0. All right. So in this Poisson bracket, the only non-zero term, only non-zero contribution comes from here. All right. So we immediately make the simplification. Px minus 3y, okay, comma, half py minus bx square is equal to 0. Right. So just by inspection, we made this immediate simplification. Okay. Now we can see a nice result here using the properties of Poisson brackets. Okay. If you don't remember, you can always derive these things. All right. What's u with v square? What is u with v square? This is basically u with vv. Okay. So that is u comma v multiplied by v plus, okay, v multiplied by u comma v. Since we are doing with classical quantities, we can just shift this v around. So this is basically equal to twice u comma v multiplied by v. All right. So we can pull this half outside. You know that you can pull the constants outside of the Poisson bracket. So this is half px minus 3y. Okay, comma. So it's u with v. Okay, I'll just write it again. Py minus bx whole square is equal to 0. Okay, so this is of the form u with v square, as we said. So it's equal to half px minus 3y. All right, px minus 3y, comma, it's u with twice u comma v. So oh, I'm sorry. All right. So we use this formula. Okay. So the formula, I'll just write it down here for further reference. U with v square. Okay, the Poisson bracket of u with v square is twice uv multiplied by v. Okay, so we can just apply that here. Okay, so this is equal to, that half is already here, this half is already there, and then you use twice. Okay, px minus 3y, comma, py minus bx, okay, multiplied by py minus bx. Okay. Right, so that's equal to this, get cancelled. So what is this? Px minus 3y with py minus bx. Again, you need to take only non-zero commutators. All right, we know that px with bx is non-zero and 3y with py is non-zero. All other terms are 0. Okay, because px with py is 0, 3y with bx is also 0. So you take the non-zero commutators, you see that this becomes px with minus bx. Okay, px with minus bx, and then you have got this minus 3y with py, okay, multiplied by py minus bx. This is equal to 0. This is our equation. Okay, now we know the fundamental Poisson brackets. What is px with x? What is px with x? What's px with x? Px with x is minus 1. So this becomes just b. This becomes just b. But I need a bracket here. What is px with x? It is equal to minus 1. We have got a minus b there. So this becomes b. Okay, and here 3y with py. Y with py is 1. So it's simply b minus 3 multiplied by py minus bx equal to 0. Now if py minus bx is equal to 0, our Hamiltonian changes. Okay, we don't want to change our Hamiltonian. We are given a Hamiltonian. Okay, so the non-trivial solution to this is b equal to 3. Okay, b equal to 3. Now if you look at the option, okay, there's only one option with b equal to 3. There's only one option with b equal to 3. Am I right? Which means that you don't have to do it again. This should be the correct answer. Okay, b is equal to 3. So option D is the correct answer. Now we can, of course, if we cannot eliminate all the options, we can of course check the other thing also. All right, we can also check the other commutator also. We can also check the other commutator, and you will see that a is equal to minus 2. Just follow exactly the same kind of steps. Okay. All right. We can go to the next problem now. That's the 6th problem today. All right. A particle of mass m and coordinate q has the Lagrangian. The Lagrangian is given. Okay, all these problems are taken from previous year net questions. All right. We have got the Lagrangian here. L equal to half mq dot square minus lambda by 2 q dot square, where lambda is a constant. The Hamiltonian of a system, the Hamiltonian of the system is given by. All right. Now there are two ways to do this. Of course, you can find the Hamiltonian by the rule h is equal to, since there is only one degree of freedom, you can write as q dot p minus l. You can of course do that. You find p and then you just do this and then eliminate all the q dot in favor of p. You will get the final answer. Okay, this is possible. But you can also do it in a different way, right? Since we are doing in a competitive examination, you have to be really quick. Okay? So you notice here that this term only has a kinetic energy, right? Kinetic energy. How do you know whether a term is a kinetic energy? If it is quadratic in velocities, right? If you have velocity square or the product of two velocities, then it's a kinetic energy term. So if you look at the Lagrangian, you see that L equal to, you can actually pull this 1 by 2, this q dot square divided by 2 outside. We just pull this q, and what you have, m minus lambda q, right? So this is quadratic in q dot this quadratic in q dot. You have got a q dot square, which means that this is a kinetic energy term. This is a kinetic energy term. There is no potential energy term. Okay. Now, in situations, there are many situations where the Hamiltonian is just the total energy. Okay, Hamiltonian is just the total energy. In that case, you don't have to do all these steps, x dot p minus L. You don't have to do it all those steps. You can save a lot of time. All right. So in this case, you see that it's only it's the kinetic energy. All right. So you also the condition that the Hamiltonian is t plus v. Okay, h equal to t plus v. If the transformation coordinates do not involve time explicitly, here there is no transformation and there is no time explicitly, so that's fine. And another thing is that the velocity has to be, sorry, the potential has to be velocity independent. Okay, so here there is no potential at all. Okay, so your answer would be just, I'll say h is equal to, let's first find the momentum. All right, p is equal to dou L by dou q dot. Okay, that's equal to, so q dot multiplied by m minus lambda q, right? Q dot multiplied by m minus lambda q, or from here you see that q dot is equal to p divided by m minus lambda q. Okay, p divided by m minus lambda q. Fine. All right. What do we do now? We have got the momentum, and we, as I said, since this only has the kinetic energy term, the Hamiltonian or the energy function is still simply the same thing, right? Q dot square by 2 m minus lambda q. That's fine, right? But the Hamiltonian should not have any q dot, so you have to eliminate these q dots in favor of p. So we have got a q dot here. We have got the expression of q dot here in terms of p. So that becomes, you just substitute this here. Okay, so that becomes p square divided by 2 m minus lambda q multiplied by m minus lambda q. Okay, now I'm sorry. So here it's m minus lambda q, but here it's m minus lambda q square, right? Because we need to find p square. Okay, so you see that the final answer is h is equal to p square divided by 2 m minus lambda q. That's your answer. Okay. Now, of course, if you are not sure whether to use this form h equal to t plus v, you can always try the other thing, x dot p minus L. Alright. In some cases, you are not really sure whether the Hamiltonian will be whether it satisfies all the conditions. Then, of course, you can always try. Alright. But here you see that the answer is p square divided by twice m minus lambda q. Right, and that answer is given here. Okay, that's option B. Option B is the answer. All right. All right. Okay, we can do one more problem. Give me a moment. Okay, so the recently discovered Higgs boson at LHC experiment has a decay mode into a photon and a Z boson, right? So this question was asked in the classical mechanics part because it's a problem that you can solve using special theory of relativity, okay? So this problem can be solved from special theory of relativity, okay? And this was asked for June 2014. So the recently discovered Higgs boson at the LHC experiment has a decay mode into a photon and a Z boson. Okay? The Higgs boson decays into a photon and a Z boson. If the rest mass of the Higgs and the Z boson are 125 GeV by c square, just a moment. So if the rest mass of the Higgs boson and the Z boson are 125 and 90, okay, the rest masses are given, right? And the decaying Higgs particle is at rest. You have got an important information, the decaying Higgs particle is at rest. The energy of the photon will approximately be, what's the energy of the photon? What's the energy of the photon, right? Now again, you can solve this problem by writing down the energy conservation and momentum conservation separately, but we are doing a competitive examination, Okay, so that means that you should find the quickest way to solve this, and the quickest way to solve this is using 4 momentum. Okay, so we can just write down the conservation of 4 momentum. The conservation of 4 momentum. Okay. The conservation of 4 momentum. Okay, so what's conservation of 4 momentum? So I'll just write the interaction here. Okay, we have got the Higgs boson. We have got the Higgs boson decaying. We have got the Higgs boson decaying into photon. I'll write it as a gamma and a Z boson. Right? It's Z0, charge is 0. Higgs boson is a chargeless particle. Right? So it's gamma plus Z. H gives gamma plus Z. Okay. Now we write the conservation of 4 momentum. Okay, so we have got the 4 momentum conservation equation. We will write the 4 momentum conservation like this. The 4 momentum of the Higgs boson, the decaying particle, is equal to sum of the 4 momenta of the photon and the what is it, the Z boson, right? And we have got this important information that the Higgs boson is at rest. We are talking about the frame in which the Higgs boson is at rest, which means that the 3 momentum, right, pH is equal to 0. Right? Now we need to eliminate the 3 momentum of pz. We need to eliminate the 3 momentum of pz. Right? How do we do that? We also need to eliminate the 3 momentum of the photon. 3 momentum of the photon. Right? Only then we will get the answer. Now how do we do that? Okay. Now one way to do this, one way that you will try, right? One way you will try is to do this. You can find pH minus pz is equal to p gamma and square, right? But squaring this will give you 0 because gamma has a 0 mass. Okay. Because 4 momentum square is, we can just square this, but squaring this will give you 0. Okay. So the convenient way to do this thing is that you just say pH minus p gamma is equal to pz. Okay. Now if you square this, you will simply get the mass of the Z boson here, and the mass of the Z boson is already given. The mass of the Z boson is already given. Right. I will show you how we do this. Right. So this 4 momentum manipulation is very convenient. Even though I explained it a lot, you notice that I have done only just one step in the problem now. This is just one step. Now you square on both sides. You square on both sides. You see pH minus p gamma square is equal to pz square. Fine, right? And we make use of the fact that 4 momentum square is equal to m square c square. Right? 4 momentum. This is one thing that you need to remember. The 4 momentum square is m square c square. It's a relativistic invariant quantity. Now you expand this. This is equal to pH square. Alright, this is equal to pH square plus p gamma square. You see that p gamma square immediately becomes 0 minus twice pH dot p gamma, that's equal to pz square. Right? These are all 4 momenta. Remember that these are all 4 momenta. So what's pH square? That is mass of the Higgs boson multi square c square. Right? Using this relation, because square of the 4 momentum is just the mass. Okay, mass square multiplied by the speed of light square. Okay, and what is p gamma square? It's the mass of the photon. It's equal to 0. Okay, and this you have to be a bit more careful. So I'll just write it like this twice. Okay, these are 4 momentum. Now I'll write it in the component form. So the pH has, let's say, the 0th component of 4 momentum is energy divided by c, and you have got the 3 momentum here. Okay, dot. Here you have, what do you have? P gamma. P gamma, it's E gamma by C, comma, P vector, right, or P gamma vector. Now you see that if you take the scalar product, now you see that if you take this scalar product, okay, if you take this scalar product, so I'll just write it here. I hope you can still see it. So mh square c square minus, okay. So take the scalar product, you multiply the components, right? You multiply the components, and it comes with a minus sign, of course, in this thing, because you know that the scalar product of 2 4 vectors is given by, this is something that you need to practice, all right? A0 B0 minus A vector dot B vector. There's a relative minus sign here between the space part and the time part. Okay, so this is minus 2. Okay, if you multiply this, EH by C, E gamma by, so that is EH E gamma by C square. All right, and what's pH? Okay, in our frame, the 3 momentum of the Higgs boson is 0 because the Higgs boson is at rest. Okay, the decaying Higgs particle is at rest. Okay, so when you multiply these two, this becomes 0. So we have eliminated p gamma. Okay, plus 0 is equal to what's pz square? That's simply mz square c square. That's it. We have done it. We just solve for E gamma now. That's what we need to find. Right? Just solve for E gamma. Okay. So you take this equation. I'll just write it down here again. What we found here was, yes, all right. Okay. So what we have here is, I'll just write it down. So what we have here is mh square c square, okay, minus twice EH E gamma by c square, right, from here. EH E gamma, twice EH E gamma by c square is equal to mz square c square. We have done it. You just solve for E gamma. We also need this EH. What is EH? We know that this is the energy of the Higgs boson, and the Higgs boson is at rest. Okay, so the Higgs boson EH is simply mh c square. Okay, mc square, because it's at rest, the rest energy. Right, so you substitute that again, you get this equation, mh square c square minus twice, this is mh c square, okay, c square, mh is the mass of the Higgs boson, and you have got this E gamma by c square is equal to mz square c square. Alright, now you just rearrange this, solve for E gamma, and you see that E gamma is equal to mh square minus mz square c square, okay, divided by 2mh. You just solve for E gamma. You just you see that it's very easy. It's mh square c square minus mz square c. You just bring this to this side and this to the other side, okay, and you solve for E gamma. Right, the c square all get cancelled, and you get this result, okay, divided by 2mh. This is the result that we need. Okay, now you just substitute numbers. Mh is given, okay, mh is given to be, mh is given in the problem, it's given to be 125 GeV by c square, okay, and mz is given by 90 GeV by c square. Right, so this c square will cancel here because we are multiplying with the c square. We are taking the corresponding energy. Okay, so it's simply 125 square. The result that you need is E gamma is equal to 125 square minus 90 square. Okay, so this is 125 GeV by c square. Right, the mass. Okay, so you are multiplying it by c square here, so that goes divided by twice. And what is mh? Twice 125. Okay, this is the answer. You just solve this and you get the answer to be 30.1 GeV. Just solve this, you get 30.1 GeV. You know how to do this numerical calculation. It's not difficult. Again, it's of the form a square minus b square. You can do it a plus b multiplied by a minus b, and just solve it. You can do it without a calculator, and you will see that the answer is 30.1 GeV, and you see that this answer is given here, right? It's 30 GeV. There's an answer 30 GeV, right? So we got it more accurately than that. It's 30 GeV. Okay, that's the correct answer. Okay. Now is your window of opportunity to win attractive prizes worth 5,000 rupees. All right. Now the ticket for your the competition, the ticket to take part in the competition, you can get it by filling the Google form link that will appear in the comment box right about now. Okay, you should see that. You fill the form, you will get the problem via your email. All right, you solve that, send it back, and then you will get the and you will potentially win a prize. Okay, so I wish you all the best. Make use of this window of opportunity, and the window will close in about 4 minutes. Okay, so till then we'll take a short break and we'll continue after you fill in the form. Okay, I wish you all the best. Alright, let's get back to our problems. Okay. Alright, so I hope you all have filled in the form and you will be able to solve the problem, I hope. So here the trick that we used, right, I just want to elaborate a little bit on the trick that we use here. The trick is to learn about four vectors, four momentum, and you combine the four momentum in such a way that the unnecessary, the terms that you need to eliminate are eliminated. Either if you are squaring it, alright, however complicated the expression for 3 momentum is, the vector part, the spatial part of the momentum is, if you square the 4 momentum, you will get the mass square multiplied by c square, alright. So you have eliminated pz vector by squaring it on this right hand side, okay, here, alright. So you have eliminated this term, pz vector, we don't know about this, we have eliminated it because we have taken the 4 momentum square and then it is simply mz square c square, alright, that's what we do. And here we have eliminated p gamma vector by combining it with ph, because we know that ph vector is 0, alright. So we have very carefully combined these terms or arranged these terms in such a way that the terms we need to eliminate are eliminated automatically. Okay, that's the convenience of using for momentum. Okay, and if you practice this, this is the quickest way to solve the problem. You don't have to write energy conservation and momentum conservation separately. Right. So I request you to practice this particular method. All right. The equation of motion of a system described by the time-dependent Lagrangian. Oh, we have got a time-dependent Lagrangian here. It's given like this. Right? What's the equation of motion? Now you know the equation of motion. It's d by dt of dou L by dou x dot minus dou L by dou x equal to 0. That's the equation of motion. Right? You just have to be careful. You just take first you take dou L by dou x dot, and that's equal to, as usual, it's mx dot, no problem there. This is the only place where x dot appears, and sorry, there's this e raised to gamma t, you shouldn't miss that, so it's e raised to gamma t multiplied by mx dot. Okay, that's dou L by dou x dot. What is dou L by dou x? Dou L by dou x is equal to e raised to gamma t multiplied by, there's a minus sign here, dou v by dou x. That's it. Okay. So this question was asked for the net exam. Maybe they wanted to confuse you using this e raised to gamma t there, but if you are careful, if you don't make the mistake that I first made here, you will get the answer. Okay. What's this d by dt of dou L by dou x dot? You see that that's equal to gamma e raised to gamma t multiplied by mx dot. Okay, you will have to use the product rule there. Right, gamma e raised to gamma t multiplied by mx dot plus, okay, e raised to gamma t multiplied by mx double dot. Okay, and dou L by dou x is again the same. So you see that the equation of motion goes like this. Just combine these terms. You can pull this e raised to gamma t outside. Right, you can pull this e raised to gamma t outside because it appears here, and it appears here. Okay, and since you need to write the equation as d by dt of dou L by dou x dot minus dou L by dou x. This is the Lagrangian. This is known as the Lagrange's equation. Right? This is equal to 0. So that minus will cancel with this minus. So you will have gamma, all right, mx dot, gamma mx dot plus mx double dot. Okay, since this minus will cancel with this minus, you will have plus dou v by dou x. This is equal to 0. This is our Euler-Lagrange's equation. Right? Now, since this multiplication factor on the right hand side is 0, this whatever is inside the parenthesis is the correct answer. Okay, do we have that answer here? Yeah, see, mx double dot, now that it's this, mx double dot, correct, plus gamma mx dot, yes, plus dv by dx equal to 0. That option is there. So option A is the correct answer. Okay. See how simple the question is. Okay. The net JRF question in December 2014. See how easily you can score a mark here. Right. You just have to be careful and do it systematically. Right. Okay, according to the special theory of relativity, the speed v of a free particle of mass m and total energy E. You need to find the velocity in terms of the energy, that's all. That's an easy problem. Okay, you need to find the velocity in terms of the energy. So what relation will you use? You will use E is equal to gamma mc square. Okay, that's the relation that you will use, and you will just solve for u or velocity from here. Okay, or you see that this is equal to 1 by square root of 1 minus v square by c square mc square. Okay, or you see that you square on both sides, E square is equal to m square c raised to 4 divided by 1 minus v square by c square. Right, now you just cross multiply and solve for v, isolate v, and you will see that v is equal to, it's not very difficult, yeah, maybe I will do it here. Okay, so this is 1 minus v square by c square, right, and you just this you can write it as, you can write this as, this is equal to m square c raised to 4 divided by c square minus v square divided by c square, right, so that c square will appear here. This is your E square. Okay, now so you see that E square multiplied by c square minus v square is equal to m square c raised to 6. Okay, now this means that E square v square is equal to E square v square, you take this E square v square to this side, is equal to E square c square minus m square c raised to 6. You just rearrange this. Okay, just rearrange this, and that's equal to, you can pull the c square outside. Okay, so that is E square minus m square c raised to 4. This is your E square v square. Right, so from here you see that v square is equal to c square E square minus m square c raised to 4 divided by E square, or v is equal to, okay, v is equal to, that's v square, you just take the square root, so that would be okay, you can just make it in the form of, I'll just do one more step, that's equal to 1 minus m square c raised to 4 divided by E square. Right, I just took this inside here. Now you take the square root. Right, v is equal to c multiplied by square root of okay, so you can write this as 1 minus mc square divided by E whole square. Right, we have just put it in the form that is given here. Right, what's the answer? So do we have this answer here? V is equal to c multiplied by square root of 1 minus mc square by E whole square. Yes, this is the answer. Okay, we have got option C as the answer. Right, c square root of 1 minus mc square by E whole square. Okay, so that is our answer. Right, I think we should leave that problem. Okay, I think we'll stop there. Right, our time has run out. It's 8:30, and this would be the last session for classical mechanics problem solving. Right, I hope you enjoyed the classes. I hope you got some insights as to how to solve problems from classical mechanics, and I wish you all the best with the problem solving competition. Okay, thank you.